Okay guys, let's continue from the same place where we have left in the previous video. By the end of that video we were discussing about the movements, its signs and its direction and its effect on the rho, that is the curvature. So slope and displacement by integration method, the equation of the elastic curve in figure 5a will be defined by the coordinates mu and x, right? So now what is mu? You can see in this figure as well, in figure 6 as well as in figure 5, that the vertical axis y-axis is defined by mu, right? So this mu is actually the measurement of the vertical deflection or displacement with respect to its original position, and the x is the length of the beam. Alright, so it says that it will be written in terms of mu and x, and so to find the deflection mu, which is a function of x, we must be able to represent the curvature 1 over rho in terms of mu and x. Okay, in most calculus books it is shown that this relationship is in the calculus books, the relation of 1 over rho, which is curvature, with the mu and x is 1 by rho is equal to d square rho mu by dx square divided by 1 plus d mu by dx whole square and whole power 3 by 2. Now substituting this into equation 2, which was derived in the last video, let me take you to equation number 2. This is the equation 2 where 1 by rho is equal to m by ei, right? So now 1 by rho is equal to m by ei, so we can replace 1 by rho with m by ei. So this term will be equal to m over ei, and it is equation 4. Apart from a few cases of simple beam geometry and loading, this equation is difficult to solve. So this equation is very difficult to solve apart from some very simple geometry and loading conditions, because it represents a non-linear second order differential equation. This is a non-linear second order differential equation. Now fortunately it can be modified. Now how it can be modified? Because most engineering design codes will restrict the maximum deflection of a beam or shaft, and the value of that deflection is very low as compared to the length of the beam or length of the shaft. Okay, consequently the slope of the elastic curve, which is determined from rate of change of mu with respect to x, the slope is d mu over dx, will be very small. Okay, and its square will be negligible compared with unity. So if you look at this equation, so this is the slope d mu over dx, right? And he says that it is very small, and when you take square of it, so the value will become very small as compared to this unity. So the value will be like 1.001, and its power 3 by 2 will almost equal to 1. So it doesn't have any effect on this whole equation. So therefore it says that its square will be negligible compared with the unity. So we ignore this value, and this whole denominator will be ignored, right, in our case. So we are now left with d square mu by dx square is equal to m by ei. See, this is our equation 5. Now we have to solve this, because this equation is in terms of bending moment. So it is possible to write this equation in two alternative forms. What are those forms? If we differentiate this, so please keep in mind that it is already a second order differential equation, d square mu by dx square. So if you differentiate it, it will be a third order, see, d cube, right? And it will be equal to shear force with in terms of x. So the bending moment, when you differentiate it with respect to the x, so that will be equal to the shear force, right? And ei, which was in the denominator, when it goes to the other side of equation, it will be in numerator, right? So again differentiating this shear force equation, so it will be the load equation. So now we are again differentiating this whole equation with respect to x. So d square over dx square, and the same value ei into d square mu by dx square, right? And this will be equal to load equation. So now we have three different equations, and those are the load equation, which is d square d power 4 mu by dx4, the shear force equation, which is d cube mu over dx cube, and the moment equation which is equal to d square mu over dx square, and as you know that ei is constant, so it is outside the what this differentiation, because it doesn't have any effect. So now to solve these equations, equation 8, 9 and 10, please keep in mind all these three equations. These are very important, right? Now to solve these, solution of any of these equations requires successive integrations to obtain this value mu, right? So that's why we use the boundary conditions. Now for each integration it is necessary to introduce a constant of integration. If you are using the moment equation, so you will need to integrate this equation 2 times, right, to remove this differential. So in order to solve the shear equation you need to integrate it 3 times, and in order to solve this equation you need to integrate it 4 times. So if you integrate it 4 times you will get 4 constants which you need to find out their values, right? So constant of integration will be introduced and then solve for all the constant to obtain a unique solution for a particular problem, right? Now the purpose of this table is just to show you, just like in the previous video I presented you, that how different support conditions affect the elastic curve or the deflected shape of the beam. It is again to just remind you that if it is a roller support, the deflection will be 0, right? Deflection will be 0 at this support. We are just talking about the support. If it is pin support, again the vertical deflection will be 0. If you term deflection as displacement, both are the same. Similarly, if roller support at the middle, the vertical deflection will be 0. If the pin support is at the middle, the vertical deflection will be 0. And only for the fixed support, see, it's a fixed end. This is the only point where deflection as well as rotation or the slope is 0. So the fixed support doesn't allow any rotation of the beam at the support, right? So these are the boundary conditions. Actually these are the boundary conditions that you can use. For example, this is x is equal to 0, the beam is starting here, so its length is 0, so mu will be equal to 0 at x is equal to 0, right? And same is the case. However, here the length will be different. For example, at x is equal to L, mu is equal to 0, and same is the case for this. Here you can put that at x is equal to 0, mu is equal to 0 and theta is equal to 0. And what is theta? Theta is actually the rate of change of mu with respect to x, right? So I have explained this slide, so you can go through it and just read it out for yourself. Now apart from the boundary conditions, we have also continuity conditions, because if the loading on the beam is discontinuous, for example this is the case, right, that is, it consists of series of several distributed and concentrated loads. This is figure 7, this is its part A, and it says that look at figure 7a. Then several functions must be written for the internal moment, each valid within the region between two discontinuities. So as you can see that from A to B the UDL is applied, from B to C there is no loading, at C there is a point load, and from C to D there is no loading applied, right? So you can take first segment from A to B, and you can call it as x1. The second segment will be from B to C, and the third segment will be from C to D. So the internal moment in regions AB, BC and CD can be written in terms of x1, x2 and x3 coordinates selected as shown in figure 7b, right? When each of these functions is integrated twice, it will produce two constants of integration, and since not all of these constants can be determined from the boundary conditions, some must be determined using continuity conditions. So there will be, for example, in case there are 3 equations, and when you just integrate them twice, so you will get 6 constants, and you cannot determine 6 constants from just these 2 boundary conditions. So you need some continuity conditions, right? For example, consider the beam in figure 8a. This is your figure 8a and this is the beam. Here 2 x coordinates are chosen with origin at A. This is your origin where x is equal to 0, right? So once the function for the slope and deflection are obtained, once you derive the equation, right, they must give the same values for the slope and deflection at point B. For example, equation 1 will be in terms of x, which is from A to B, and equation 2 will be in terms of x2, which will be from B to C. But it says that both the equations will give you same value at this point. Why? Because the beam is a continuum, right? It is not consist of two different segments. It is a single beam, and the rho will be same for both the equations. So expressed mathematically, the continuity conditions will be what? That theta at theta 1 at A is equal to theta 2 at A. So this is the point where your x is equal to A, right? See, for example, if the whole length is L and this part is A, this part of length is B. So when you are going up to this much distance, the distance is A. So at this point, at distance A, your slope, this is your slope, right? This is your theta. So when you measure your slope with this equation, theta 1, A1 represents your first segment. So theta 1 at A will be equal to theta 2 at A. Similarly, the mu 1 at A will be equal to mu 2 at A. So both the deflection and rotation or the slope at this point for both the equations will be same, and this is your continuity conditions. I hope when we will solve the numericals you will better understand the concept. They are used to evaluate the two constants of integration, right? Once these functions and the constants of integration are determined, they will then give the slope and deflection, which is the elastic curve, the very first concept of this chapter, for each region of the beam for which they are valid. Okay, so very briefly we will discuss about the sign convention and coordinates, and then we will jump to the example 1. Okay, so as we previously discussed that this sign convention will be taken as positive, right, for the bending moment, and when applying equations 8 through 10, if you remember, equation 8 was for the load diagram and 10 was for the bending moment diagram. It is important to use the proper signs for W, V or M as established for the derivation of these equations, right? Also, since positive deflection mu is upwards, then positive slope theta will be measured counterclockwise. As you can see that if it is deflected in an upward direction, then its theta is measured in the counterclockwise direction, right, when you are from the left side, because a positive increase dx and d mu creates an increased theta that is counterclockwise, right? Similarly, if positive x is directed to the left, then theta will be positive clockwise. For example, if you are coming from the right and it is to your left, so then in this case, see, the theta is in clockwise direction and it is taken as positive, right? Now, since we have considered that d mu over dx is equal to 0, the original horizontal length of the beam's axis and the length of the arc of its elastic curve will almost be the same, because the change in the deflection with respect to x is 0. In other words, ds in figure 8c and d, this is 8c and this is 8d, is approximately equal to dx, right? So your ds, which is the length of this arc, is equal to its horizontal component. The ds is the hypotenuse and dx is the base. So therefore ds is equal to dx square plus dv square. This is a Pythagoras theorem, right? And when you take dx as a common, so it is 1 plus d mu over dx whole square, and dx can be taken outside the bracket, outside this under root, because the square can cancel it, and which is almost equal to dx. So your ds is almost equal to dx, because this value is almost equal to unity. Why? Because here we says that d mu over dx is equal to 0. So if you put 0 in here, so it's almost equal to 1. So as a result, points on the elastic curve will only be displaced vertically and not horizontally. So it means that the points, for example, these points are disturbed vertically and not horizontally. Okay, their length will remain same, but their elevation or their height will be different. Also, since the slope theta will be very small, its value in radians can be determined directly from theta almost equal to tan theta, which is almost equal to d mu over dx, right? This is the procedure for the analysis, and you can read it by pausing this video. Let me take you to the example 1. The example says that the simply supported beam shown in figure 9a, this is your figure 9a, subjected to a concentrated force of 6 kilonewton at a distance of 2 meter from the support A. Determine the maximum deflection of the beam. EI is constant, your flexural rigidity is constant. You can take two sections, x1 which can be from this point A to point B, and x2 which is from point B to point C. Now the limit of x1 is 0 to 2 meter, right, and the limit of x2 is from 2 to 3 meter, right? So solution says that the beam deflects as shown in figure 9b. The beam will deflect in this way, right? We all know that as per knowledge of our previous video. The deflection is mu at d, and we assume that the maximum deflection is happening at this point d. We don't know the location of this point. It can be here, it can be here, whatever the location is, but we are assuming that d is that point where the maximum deflection is happening, and at the maximum deflection the curve is horizontal and its slope is 0, right? So two coordinates must be used since the moment function will change at b. So from here the moment function will change. So x1 will be from 0 to 2 as I explained earlier, and x2 is 2 to 3. So from the free body diagram shown in figure 9c, m1 will be equal to 2 into x1. See, when we take the section at this side of the load, so there is only this reaction. So the reaction is 2 kilonewton and the distance is x1, so moment will be equal to 2 into x1, right? And for m2, when you take the section at here, so you have this reaction and you have this applied load. So when you take the moment, this is equal to 2 into x2 minus 6 into this distance, which is x2 minus 2 meter. So you got these two values, these two equations for bending moment, right? Now applying equation 10 for m1, and m1 limits is 0 to 2, right, and integrating twice gives us, for example, this is your m1 equation 10. M1 is equal to ei d square rho 1 divided by dx1, not rho but mu, divided by dx1 square is equal to 2 into x1, right? So when we integrate this, the d square is converted to d mu 1 divided by dx1, right? And when we solve this to x1, we integrate it, so the power is 2 and we divide it by 2, so 2 is cancelled with this 2, so x1 square is there and a constant will be added to this equation, if you know the procedure of integration, right? So now when you again integrate this, because still there is a rate of change of rho 1 with mu 1 with respect to x1, so when you do it ei rho 1, now this equation gives you the value of rho 1, there is no derivatives, right? So mu 1, sorry, it's mu 1 not rho 1, mu 1 is equal to when you integrate this x1 square, so it will gives you x1 cube by 3 plus c1 x1 plus c2, another constant appears in this equation. So now we got two equations, one is for the slope and one is for the deflection, and we got two constants, one is c1 and other is c2, and we know the limits of x1. Likewise for m2, the limits are from 2 to 3, and again in the same way you can put the value of m2 equation, which is d square mu 2 divided by dx2 square, and this is equal to, when you solve this equation, it is equal to 4 into 3 minus x2, right? So 4 into 3 minus x2, and when you integrate it, so this is the first integration and a constant will be added, which is c3, and when you again integrate it, so the equation will be like this, and another constant, which is c4, appears. So now there are 4 equations and 4 unknowns, c1, c2, c3 and c3, c4. So we apply the boundary conditions as well as the continuity conditions to solve these equations, right? We know the boundary conditions. So the 4 constants are evaluated using 2 boundary conditions, namely, see, in this beam you have two boundary conditions. For example, at x is equal to 0 the rho is 0. You can see that here the deflection is 0. Also at x is equal to at c x is equal to 3 rho is also 0, right? So you have two boundary conditions, x1 is equal to 0, rho 1 is equal mu1 is equal to 0, it's mu. And when x2 is equal to 3 mu2 is equal to 0. So these are the two boundary conditions that we can put. Also two continuity conditions must be applied at b. For example, at b we can at this point we can apply the continuity conditions, and what are that? We can say that the slope of the first part, that is d mu1 by dx1 will be equal to d mu2 divided by dx2, right? And it is well known because it is a continuous beam and the slope will be same if you come from this side or from this side. So at x1 is equal to x2 is equal to 2 meter. This is your first continuity condition. And the second continuity condition is mu1 is equal to mu2 at x1 is equal to x2 is equal to 2 meter. And it is quite understandable that at b the mu will be same if you use any of the equation, right? So we can use these four equations. For example, mu1 is equal to 0, this is the first boundary condition. When mu1 is equal to 0 and x1 is equal to 0, so if you put it in this equation, so your this equation is, if you put 0 here, 0 here, 0 here, so you are only left with c2, right? So the equation 2 comes out that c2 is equal to 0. Another boundary condition that mu2 is equal to 0 at x2 is equal to 3. So if you put it in this equation 4, so it turns out to be like this. Now another equation, another condition, continuity condition, is about the slope at 2 meter. So you can use equation 1 which is about the slope, see d mu1 divided by dx1, and equation 3 which is about slope d mu2 divided by dx2. So it says that at x is equal to 2 both are same. So you put the values, you put the value of x which is 2 here and x which is 2 here in both equation 1 and equation 3. So you go on and solve it. Also the other continuity condition was that at x is equal to 2 mu1 and mu2 are equal or are same. So you use the condition of equation 2 and 4 because these are for the deflections mu1 and mu2. So equation 2 is equal to equation 4 where at x is equal to 2, right? So these are the four equations with the values put it in it, and when you solve them you got c1 is equal to minus 8 by 3, c2 is equal to 0 which is quite obvious, right? c3 is equal to minus 44 by 3 and c4 is equal to 8. Thus these equations become, when you put these constants c1, c2, c3, c4 in these equations, so you got the values like this. These are the four equations. Now equation 5, 6, 7 and 8 are your new equations. So by inspection of the elastic curve, figure 9b, this is your 9b, this one, this is your elastic curve, right? The maximum deflection occurs at D, which is somewhere within region AB, right? So here the slope must be 0. So please remember that the maximum deflection occurs where the slope is 0. So where is that point? You just use the first side because it is in the AB region. So the slope must be 0. This is your slope equation, right? So make it 0 and x1 square minus 8 by 3 is equal to 0. So it gives you that at x1 is equal to minus 1.633 your deflection will be maximum. Now substitute it in equation 6 and you will get the maximum deflection. So you got the distance from the slope equation and you put it into the deflection equation and you got the maximum deflection, which is at 1.633 meters. So the negative sign indicates that the deflection is downwards. Alright. So we are now moving to the next example, and in this example, in this beam, in this example the beam is different and it is a continuous or overhanging beam, and the point load is applied at the overhanging part. Okay, there are two spans, 2-meter span which is between two supports, and a 1-meter span, right? So there will be two conditions or two limits, x1 which will be from support A to B, and x2 will be you can either take it from support B to the point load, or you can take it from the point load to support B. Okay, so in this case we are taking it from the free end, which is point C, or the point load, and the beam deflects into the shape shown in figure 10a. You can see the deflected shape, right? Due to the loading, two x coordinates will be considered, namely x1 which is from 0 to 2, right, and x2 which will be from 0 to 1. So in this case we are taking this as 0, and till here it is 1. So from C to B it is 0 to 1, right? We are not taking it from point A. In that case it would be from 2 to 3. So x2 is directed to the left from C, since the internal moment is easy to formulate in this way. Okay, now finding the moment functions using the free body diagram for x1. First, for this 4 kilonewton we have to find the reactions. So the reaction is 2 kilonewton is downward at this support A, and there will be a 6 kilonewton upward force at support B, right? So using the free body diagram, just take a section at x1, and the moment will be minus 2 into x1, right? Similarly, take a section at x2, and the moment will be minus 4 into x2. But why it is? Because the resulting moment will be in the downward direction in both the cases. So the slope and elastic curve. So applying equation 10, which was the moment equation, the second order differential equation, this one, moment is equal to minus 2x1, right? So instead of m1 we have written it in the form of equation 10, and similarly the other moment m2. So the limit is that it is from 0 to 2 and it is from 0 to 1. Just integrating this equation with respect to x will give us x1 square plus c1, and again integrating it. So this is our slope equation, equation 1, and this is our deflection equation, equation 2, and c1 and c2 are the constants that are obtained after double integration of this equation, this moment equation. Similarly, for the second segment, when we integrate this equation, we will get c3, and double integrating this will give us c3 and c4. So the four constants, just like in the previous example, are determined using three boundary conditions. What are the three boundary conditions in this case? Number one is the mu is 0 at x is equal to 0, right? Here x1 is 0 and mu is 0, so there is no deflection or vertical movement. Similarly here, mu is 0 at x is equal to 2, x1 is equal to 2 or x2 is equal to 1. So mu1 is equal to 0 at x1 is equal to 2, and mu2 is equal to 0 at x2 is equal to 1, right? So these are the three limits or three boundary conditions, and we can have one continuity condition. And what is that? The continuity of slope at the roller requires that the slope at roller is same if you come from this side or you come from this side. So at x2 is equal to 2, or sorry, x1 is equal to 2 or x2 is equal to 1, the slope will be equal, right? This is our continuity condition. D mu1 by dx1 is equal to minus d mu2 divided by dx2 at x1 is equal to 2 meter and x2 is equal to 1 meter. There is a negative sign if you see, because the slope is measured positive counterclockwise from the right and positive clockwise from the left, which we discussed, right? So here is not the case, and we are not measuring it in the clockwise direction, we are measuring it in the counterclockwise direction, so it is negative. So therefore mu1 is equal to mu2 is equal to 0 at x1 is equal to 2 and x2 is equal to 1. Applying these four conditions yields, now applying these four conditions, three boundary conditions and one continuity condition, it says that mu1 is equal to 0 and x1 is equal to 0. So here when your x1 is equal to 0 and mu1 is 0, so 0 0 0 will gives you the value of C2, which is equal to 0. Similarly, mu1 is equal to 0 and at x1 is equal to 2. So again put the values of mu1 and x1 is equal to 2 in this equation, right? And in this equation you know the value of C2. So if you put the value of C2 is equal to 0, you will get the value of C1. Similarly, you know that the third boundary condition is mu2 is equal to 0 and x2 is equal to 1 meter. So putting this in equation 4, which is about mu2, so you will get this equation, right? Now the unknown is C3 and C4. So you have a continuity equation, which is the slope of mu1 at x is equal to 2 meter is equal to the slope of mu2 at x is equal to 1 meter. So putting the values, this is the slope, so minus x1 square plus c1, this is minus x1 square plus c1 is equal to, this is the second slope equation, which is minus 2 into x2 square plus c3. So here mu1 the x is 2, so you have put it 2, here the x is equal to 1, so you have put it 1, right? Now solving these, we obtained C1 is equal to 4 very easily. If you put C2 is equal to 0 from this equation into this equation, you will get the value of C1. So C1 and C2 can be found very easily. Also if you put the value of C1 from this equation into this equation, you can get the value of C3, and putting the value of C3 in this equation, you can get the value of C4. So you know all the values of 4 constants. Substituting the C3 and C4 into equation 4. What was the equation 4? This is your equation 4, right? Why we are using equation 4? Because if you can see that the maximum deflection is at the point of application of load at the free end, or in the question it also mentioned that determine the displacement at C. So at point C you have to find this displacement or deflection. So for that you have to use equation 4, which is about the deflection in the second segment, right, in the segment BC. So at point C you can find the deflection by using the equation 4. Okay, so substituting C3 and C4 into equation 4 gives, this is your equation 4, and you have put the value of C3 and C4. C3 was 14 by 3 and C4 was 4. So the displacement at C is determined by setting x2 is equal to 0. Why? Because x2 we have taken it from this free point. So at this point x2 is equal to 0, and when you come to support B, x2 is equal to 1. So here x2 is 0, so put x2 is equal to 0. We get, put x2 is 0 in this equation, so you will get the mu C is equal to this 4 minus 4, right? So this is our answer. This is our answer of the displacement or deflection at this point C, right? So that's how we determined the deflection at the free end where the point load was applied. Now we are only left with the statically indeterminate beams, and we will solve it by method of integration, and we will solve an example on it, and that will be the end of this lecture and the video as well. So it says that in indeterminate beams the reactions are not known. For example, in this case the reactions could be determined from the equilibrium equations, but in the indeterminate beams you cannot get the reaction, right? So consider the beam is subjected to distributed load. This is a UVL, right, and it is applied to this indeterminate beam whose one end is fixed and the other end is pinned. Determine the reaction at A. Now you have to determine the reaction at A. So the beam deflects as shown. See, this is the deflected shape of this beam. Here the slope is 0 as well as the deflection is 0. However, here the slope is there but the deflection is 0. Only one coordinate x is needed. So as you know that the load is continuous, so there is only one coordinate x. There is no need of x1 and x2. For convenience we will take it directed to the right from left to right, right, since the internal moment is easy to formulate. Also the beam is indeterminate to the first degree, as there is only one redundant. So if we choose the segment shown in figure 11c, if you draw the reactions, so there is one unknown reaction ay here and two unknown reactions by and mb here. So 3 minus 2 is 1, we are left with only 1. So just take a section at any point, okay, and this will be your diagram at that section. Here you don't know the value of ay, right? Also the arbitrary applied load is there, which is W naught. So there is no given value of W naught. So the internal moment M will be a function of x, written in terms of the redundant force Ay, right? So the bending moment equation will be equal to, what is the bending moment value here? It will be equal to Ay into this x, right, minus this force. What is the magnitude of this force? This will be equal to, for example, the total force is equal to W naught into L divided by 2, since it is a triangular force. So the magnitude or the resultant is half into W naught into L. And when we are talking about this segment, so it will be equal to half of W naught into x square by L. Alright, so this force half W naught x square by L is acting at a distance 1/3 of the x, right? So the x multiplied with x square will be x cube, and 1/3 into 1 by 2 will give you 1 by 6. So this is your equation of moment, Ay into x minus 1 by 6 of W naught into x cube by L. And now you have to solve this M with that equation 8, if you remember, sorry, equation 10, which is equal to Ei into d square mu divided by dx square, and it is equal to this what we have got just now. And just integrate it with respect to x and you will get C1, right? You have solved this. X will become to x square by 2 and x cube will become x4 by 4, and when you multiply 4 with 6 is 24. So when you again integrate it for this mu value, you will get x cube, you will get x5, you will get x and another constant. So the three unknowns, which are Ay, C1 and C2, are determined from the three boundary conditions. What are those boundary conditions? As I explained earlier, that at x is equal to 0, mu is equal to 0 here. Here x is equal to 0 and mu is equal to 0. Also at B, where x is equal to L, mu is equal to 0. See, at x is equal to L, the mu is equal to 0 as well as the slope is equal to 0, which is equal to rate of change of mu with respect to x. So applying these equations to these conditions to these equations, we will get x is equal to 0, mu is equal to 0. So put mu is equal to 0 and x is equal to 0 in this equation, you will get C2 is equal to 0. Also you put x is equal to L, and once you put the slope is equal to 0, and then you put mu is equal to 0 at x is equal to L. So put here slope is equal to 0 and x is equal to L in this equation. So you will get this, and when you put x is equal to L in this equation and put mu is equal to 0, so you will get this one. So now you know the value of C2, right? From here you can get the value of C1 in terms of Ay. Also if you put C2 here, you can get the value of C1 in terms of Ay, or vice versa, you can get the value of Ay in terms of C1, right? So solving, you have two unknowns Ay and C1, and you have two equations Ay and C1. So these two equations can be solved, and the values of unknowns Ay and C1 can be determined. So Ay is equal to 1 by 10 of W naught into L, and similarly C1 is equal to minus 1 by 20 of W naught into L cube, and C2 is equal to, as we know, that is equal to 0. So in this way we have determined the value of support reaction, the extra reaction that we needed to know. Now as we know that Ay, we know the value of Ay, so we can easily determine the reactions at B, and in this way we can solve this beam or this indeterminate structure, right? So using the result for Ay, the reactions at B can now be determined, as I explained. Show that Bx is equal to 0, By is equal to this, and Mb is equal to this by solving the beam for the other support reactions. So in this way you have found the reactions of the beam, which was indeterminate, and I hope that you have learned the concept of deflection and how to measure the deflection and slope, and how to use the equations, the equilibrium equations, the continuity equations, and that's all. So thank you very much, and see you in the next video.